Okay, this is a remade version of Chapter 11. And Chapter 11 is controlling microbes from outside and within the body. Okay, so after reading this chapter, you should be able to compare the 5 physical methods used to control microbial growth, identify the general principle used in disinfection, describe the different chemical agents and gases used to control microbial growth, recall the early history of antibiotics, explain the actions of penicillin and the development of penicillin resistance, identify the mode of action of other antibiotics, and assessing the challenges of antibiotic resistance in the medical field and the identity and abuse and misuse of antibiotics today. Okay. Cleanliness, sanitation, and antibiotics. Um, Hand washing and sanitation helps minimize disease transmission. And one of the things that um, I'm a big proponent of is washing your hands well. Okay, washing your hands well. This should be one of the things you take out of this class is when to wash your hands. Um, Antibiotics have revolutionized medicine and our ability to cure infectious disease. Okay, physical methods from hot to cold. So we can either use moist or dry heat, and we can often use these methods to sterilize whatever we are trying to deal with. Sterilization is a complete lack of microbes. Okay, there's nothing alive in when something is sterilized. And like it says, all forms of life. Okay, and we can do this in a couple of different ways. When you're thinking of um, temperature, um, we can raise the temperature so that we can kill all the microbes. So when you're using moist heat, you're going to be denaturing all the proteins, and you'll also be disrupting cell membranes. Now, the machine that is used most often to sterilize things is a pressure cooker, or sorry, an autoclave. An autoclave is really just a fancy pressure cooker. Um, it's a two-layer system, and hopefully I can get this animation to play. Okay. Um, the ideal standard for an autoclave is to heat to 121 degrees centigrade, and that is done under pressure at 15 psi, pounds per square inch, and that has to be for 15 minutes. Okay, so the heated air can go in and then go into the chamber, and then once the air is evacuated, it can go out through and exit. Now, pasteurization, and you've almost assuredly seen pasteurization on the milk in your house. Pasteurization does not sterilize. Okay, so there's still microbes that are alive in pasteurized milk. Now we can do the pasteurization a couple of different ways. We can either use a holding method, where we would heat to 63 degrees centigrade for 30 minutes, or a flash method where you'd heat to 72 degrees centigrade for 15 seconds, or an ultra-high temperature method where we go up to 140 degrees centigrade for just 3 seconds. Okay. Um, and This ultra-high temperature method may sterilize if you put the product into a sterilized container when you're done with it. Now, in dry heat methods, you need to sterilize. You need to get to between 160 to 170 degrees centigrade to be able to sterilize the material. And this is basically done in an oven. It can also be done in an incineration. As we're working at the bench top, I'll be sterilizing a inoculating loop or something that we use to manipulate the bacteria by doing incineration in a Bunsen burner. Now, leaving the heat methods behind, we can also go into radiation. And radiation is just a form of rays, um, and we have a number of different kinds of rays. Obviously, light is a type of ray, but we can have ultraviolet, cosmic X-rays, um, microwaves. Those are all waves which can be used for sterilization. And in general, the shorter the wavelength, the more toxic it is to the bacteria. So a very simple method that almost everyone can have at home is to have something like ultraviolet light, and the ultraviolet light will kill, and is certainly much more effective than just white light. Okay, so ultraviolet radiation, and what you're doing with your UV light is you're disrupting the DNA. Uh, you'll get a lot of errors in the DNA, and it gets so many misformed bases that you just can't replicate through it. Ionizing radiation, these will include things like X-rays, gamma rays, and these can be used to generate a pasteurizing dose uh, for irradiated food. And just a sort of side note, a lot of times people will see that a food is sterilized or pasteurized by radiation. The radiation does not stay around. Okay, so while it could sterilize the food, it's not there anymore. And I think that's a common misconception. People think, oh, well, I don't want food that has radiation coming off of it. Well, it doesn't have radiation coming off of it. It was just pasteurized uh, with the radiation. We can also dry out substances to get them to sterilize. Okay. So that's the science of desiccation, and it's making the amount of water just too low to be able to support life. In a laboratory, you can do something called lyophilization, where you're freeze drying the sample, and again, that will remove so much water, and plus the freezing is going to keep anything from living. Salt and sugar are also two great ways of desiccating something. And you can think about that something like a meat, like bacon, which is cured with salt, or something like fruit cocktail, where you have a lot of fruit. You have the fruit, but you have a lot of sugar in that fruit cocktail, and that's going to keep any of the bacteria from growing because there's just not enough water around. If you take up all the space with salt or sugar, then the only thing there's no room for any microbes to grow. Now, a method that is used in the laboratory a lot, and we use it mostly for things that are temperature sensitive, is filtration. Okay, but filtration are very specialized methods of making these filters. Okay. Um, so, like you can see there in the picture, you can have a filter in that upper flask, and you can pour sterile, non-sterile liquids in the top, and then what gets pulled through the filter will be sterilized because all the bacteria will be trapped onto the filter. Um, you can have high efficiency particle air filters um, for things like HVAC systems, um, and they, of course, will sterilize the air that's coming in. Uh, the only problem there is that you have to clean those types of filters fairly often because things that are in the air are going to get stuck onto the filter, and that will reduce the efficiency of the filter. Okay. Low temperature. So in addition to high temperature being used to sterilize things, we can also use low temperatures. So in general, um, one of the reasons you put things in a refrigerator is to lower the temperature such that the bacteria can't grow in them. If we want to do a little more uh, lower, we can go to a freezing temperature um, where the material is frozen so that the bacteria can't grow there. Okay, chemical methods of growth control, antiseptics, and disinfectants. So in general, disinfection is a method of lowering the population of the microbes, um, and it might not necessarily get all the pathogens. Okay, so if you say disinfect a surface with, say, a household cleaner, disinfectants um, and antiseptics are both chemicals that can be used for disinfection and microbial growth control. Um, Disinfectants are going to be able to lower the microbial population, where antiseptics most times will be able to essentially get rid of all the microbes. Um, some of the general characteristics of an ideal chemical agent, and I'm not going to read the entire list to you, but let's just point out some of them. You want to be able to kill all types of microbes. You want something that cleans, that's going to be able to dissolve in water. Um, you also want it to be fairly stable for a fairly long time. Okay, and of course you don't want it to be toxic to the human who is using it. So I would look over this list a little bit more, but just uh, keep some of those things in mind as you're designing the ideal chemical agent. Alcohols and peroxides. Uh, Alcohols are going to disrupt the cell membranes and denature the proteins. And alcohol or ethanol is sort of your go-to method. Isopropyl or rubbing alcohol is another good one. The advantage of ethanol is that it's safe to humans if the human should consume it. Isopropanol is not safe for humans. If you consume isopropanol, you run a very high chance of blindness. Okay. Hydrogen peroxide is an ideal cleaning agent. Uh, Benzoyl peroxide is also used. Um, Again, on the more maybe industrial side, halogens um, like iodine are something that's going to kill a lot of microbes. That's one of the steps. Say you're going to do surgery before you make the incision. You're going to clean with iodine. Okay. Um, Chloroxide, or sorry, chlorine is going to be another halogen that's going to be very effective at killing microbes. Silver is a very effective killer. Um, I've done an experiment in my lab where we actually handed out pens uh, to people, and we had some silver tape on one side and copper tape on another side. Um, and we're able to show that the side with the silver tape didn't have any microbes left on it. Soaps and detergents. Uh, Soaps are wetting agents, and like I said previously, uh, being able to wash your hands with soap and water is always a very good method of cleaning your hands. Okay, you're getting rid of all the microbes, and you're also doing some cleaning. Um, a huge advantage, I think, of uh, washing under uh, running water is that you're able to clean or rinse away all the microbes. A lot of people will say use hand sanitizer, but when you use hand sanitizer, that alcohol in there is going to kill the microbes, but it's going to leave them on your skin. Whereas hand sanitizer will kill, but you run the risk of having the microbes sitting on your hands. Whereas if you wash with soap and water, you're going to kill the microbes and then rinse them away with the running water. Uh, Quaternary ammonias um, can be used as a disinfectant or an antiseptic. And for example, mouthwashes are very often used or have these properties. Phenols are very expensive. Carbonic acid, sort of your basic phenol, um, are going to kill the microbes very effectively, but start being a little more dangerous. Um, Early in the development of microbiology, Joseph Lister used carbolic acid as his sterilizing agent so he could do sterile surgeries. And so he would squirt the phenol into the air and onto the body of what he was about to have do surgery on. so that he could have a clean operating surface. Uh, Triclosan is a phenol that is used pretty extensively nowadays. Uh, you can find triclosan in many, many products. Um, it's not terrible. You can even find triclosan in some uh, toothpaste, and that can really kill a lot of microbes in your mouth if you would use that. Aldehydes and ethylene oxide. Um, Again, uh, alcohols that are quite uh, detrimental to the bacteria. A formaldehyde, which is sort of your standard, oh, that's what will preserve something in. Um, and those of you who have had classes where you have to dissect something, you almost always have the sample that you're going to dissect, the animal that you're going to dissect, stored in formaldehyde. Okay, glutaraldehyde, just another derivative of formaldehyde. Uh, Ethylene oxide is a sterilizing gas. Okay, let's talk about antimicrobial drugs. Those include things like antibiotics, which are the sort of first thing you think of when we think of antimicrobial drugs. Um, Paul Ehrlich was one of the first persons to discover or even conceive of antibiotics. And what Ehrlich said was that these things were magic bullets. And so what he was saying was that these drugs would act specifically on the microbes and not kill the other person. So they were a real magic bullet because it will only kill the microbes. Okay. Um, Salvarsan was one of the first things to be used, and that was in the treatment of syphilis. Uh, Domagote, uh, he used a compound called Prosil, and he also used sulfonamides to treat streptococcus and staphylococcus infections. Sal Waxman, who also has a relationship to New Jersey, is the first user of streptomycin, and he coined the term antibiotic. So an antibiotic is that it's going to kill the bacteria um, and not kill uh, eukaryotic cells. Penicillin was developed by the work of Alexander Fleming, and what Fleming noticed was after he went on vacation that he had this mold on this plate and then a bunch of bacterial colonies. The bacterial colonies didn't really line up very well, or they didn't grow very well near the mold. And so he thought that the mold might be producing something that was keeping the bacteria from growing. Okay. He later found out that drug was penicillin. Howard Florey and Ernst Chain were able to get a method for being able to purify it, and Fleming, Florey, and Chain all shared the Nobel Prize for the development of penicillin. Okay, so penicillin is a beta-lactam, and when you look down here at the natural structure, you can see that you have this five-membered ring with a four-membered ring, and so that is really the beta-lactam part. That's the sort of core part that does the majority of the killing. And then at the end of that, we can have some sort of derivative. Okay, and there are a number of different derivatives, and these different derivatives can do things like absorb in the body faster or be more stable um, in in the body. Um, they can also be sometimes they can be used to be resistant to some of the antipenicillin uh, resistance factors. Um, but the penicillins all have this beta-lactam structure as the main thing that is causing them to do the killing. And the way that it's killing the cells, it's interfering with cell wall synthesis. So obviously a cell that doesn't have a cell wall can't survive very well. Um, because a gram-positive bacteria have so much more cell wall, um, the penicillins are very effective against gram-positive bacteria. And we can get resistance to penicillin by penicillinases. And these are compounds that are going to be able to break down the beta-lactam ring. Okay, cephalosporins and aminoglycosides. Cephalosporin is one of those antibiotics, and it is going to also interfere with cell wall synthesis. It is effective against gram-positive bacteria, aminoglycosides, uh, which is produced by some species of streptomycin, and they are effective against gram-negative bacteria. So between the cephalosporins and the aminoglycosides, we have the ability to cure both gram-positive and gram-negative infections. The aminoglycosides in general inhibit protein synthesis. So if something is a broad-spectrum antibiotic, that means it kills both gram-positive and gram-negative bacteria. Um, the gram-positives are mostly the broad spectrums are going to be able to inhibit protein synthesis, and it's interesting that is the target because uh, every cell has to be able to make its own proteins, and so if you can inhibit, it doesn't matter, how thick the cell wall is, you still have to make protein. So that's why protein synthesis inhibitors are very good at being broad spectrum antibiotics. Chloramphenicol and tetracycline are two of those. Um, Tetracycline is not really used much in humans anymore because there's been a whole lot of animal use of tetracycline, and there are just too many tetracycline resistant organisms out there. Um, So again, we can have antibiotics that are protein synthesis inhibitors, erythromax, um, bactracin, um, zithromax. You can have cell wall synthesis inhibitors, vancomycin, which is your sort of last result antibiotic. Okay, um, when a doctor gives out antibiotics, the very last thing they want to give someone is vancomycin because it needs to be the drug that's saved for the very last chance of having any antibiotic that will work. When I had an infection in my leg, I was on vancomycin for about 4 months because they just couldn't cure the infection. Um, and I don't know how many of you have actually seen me. Um, I'm the guy who walks around with one leg. I have a prosthesis leg because I had to get my leg cut off because the infection was so bad. We can have RNA synthesis inhibitors. Rifampin is one of the major drugs there. We can inhibit DNA synthesis replication. Uh, Cipro is probably the best known of that class of drugs. Or we can have topicals that you can only apply on your skin, and bactracin or polymyxin B are two that are the most common there. Uh, when you have triple antibiotic cream, um, bactracin and polymyxin are in that cream. So these all up here, okay? And you can look at these. So as you look at the antibiotic targets, um, as long as you can pick something that is different in bacteria than in a eukaryotic cell, you can then discover a magic bullet. Okay, we've seen a number of times, um, again in the penicillins, something like cell wall synthesis. So that cell wall is totally unique to bacteria. It, it's not found in eukaryotic cells. Um, then you can go to other things like cell membrane or DNA synthesis. And again, those are things that we can specialize in, that are specialized to the bacteria that human cells don't do. Antiviral, antifungal, and antiprotozoan drugs um, are very, very difficult. Okay. Um, we do have a few drugs that are for things like AIDS or hepatitis. Uh, but again, there's not as much um, specific that are more specific to the viruses because the viruses have to take over your cells to be able to work. So it's really difficult to have something that is a magic bullet for a virus. Um, and antifungal drugs um, can be very difficult. Again, yeast infection, athlete's foot, ringworm, again, all somewhat treatable infectious disease, but uh, they take a whole lot of time because they're kind of specialized. We have to find something that's specific to the infection to get them to be able to kill. Okay. Um, the biggest antiprotozoan drug that we need to worry about is with malaria. Um, and some of the quinones can do that, but again, very very hard to treat because those cell types are so similar to our cell types. Okay. Antibiotic resistance. So antibiotic resistance is a huge problem nowadays. Okay. And antimicrobial resistance refers that resistance to the drug therapy that you can no longer kill them. And like was pointed out before, in the case of the penicillins, penicillinase is able to break down that drug, so we get antibiotic resistance because we have another compound in the cell that is able to break down uh, the beta lactam. And one of the things when you have an antibiotic resistant drug, okay, you can start off with a population of cells, and then one of those can become resistant, okay, and if we give the drug, then the cells will die, and only those that are resistant would be able to survive. Okay. So here, in this case, um, we have the green, which are the susceptible ones. We have a few that have become antibiotic resistant. And then when you give the antibiotic, um, the susceptible ones will still die, but the ones that are resistant will go on and multiply. And that's one of the reasons why it's really important to take antibiotics for the prescribed time and at the exact time that you should be taking them. Um, so antibiotic resistance is a huge problem because it can kill the human if you don't find any other agent to kill that microbe. Um, so, for example, the infection that was in my foot, we went to vancomycin because we couldn't find anything that was killing the bacteria that was in my ankle. Um, and antibiotic resistance certainly prolongs illness and can be an increase in the amount of death that someone can have from the infections. Um, so there are a number of uh, bacteria that become resistant to different drugs. Now, let's you look at that list. The list is in your book also. Um, and just know that you can't treat the drug or you can't treat the infection anymore once you run out of something that the cells are sensitive to. And a lot of people have labeled this in maybe around year 2000 as the post-antibiotic era. So from 1928 to 2000, when Fleming's penicillin took over. Okay, that was the antibiotic era, and we could treat a lot of diseases effectively. But now we're getting so much antibiotic resistance that we're really in a post-antibiotic era. Um, One thing that happens kind of commonly is that once you're resistant to one bacteria, or sorry, to one antimicrobial, you might become resistant to many, many antibiotics, making a multi-drug resistant uh, bacteria. And multi-drug resistant tuberculosis is one thing that's really quite prevalent. So the people, they might be put on a first drug, and then we find out that the person's uh, the bacteria are resistant to that. Then we try another drug, and you find out that they're resistant to that too. And so the illness is prolonged for a long time because we can't find any agent that we're not resistant to. And one of the most common things that happens is that doctors will see a patient, and to make the patient feel better, they'll give some antibiotics. But let's say you had a viral infection. Okay, if you have a cold from a virus, um, that the antibiotics can't work against the virus. Okay, so you end up giving an antibiotic for something that's not going to work, and that is a real problem. Um, that there's that overprescription of antibiotics because in general the antibiotics are fairly cheap and it makes people feel better and makes them feel like they're doing something for the disease they have. Okay, so to get rid of this multi-drug resistance, um, we can preserve the antibiotics that we still have. Um, okay, and like I said, don't use antibiotics for viral infections. Um, take the antibiotic for the amount of time that you're supposed to. Um, don't share antibiotics and don't save antibiotics for if you get sick again, because we all know that you want to get better, but the doctor has specifically chosen that first antibiotic to treat the disease that you have. Um, one thing that is uh, very kind of difficult to do is we need to develop new um, antibiotics, and there used to be antibiotics used to uh, be a major focus of pharmaceutical companies, but nowadays, since we had that sort of era where we had drugs that always worked, we have stopped developing new drugs. Okay, so what should we have learned from this lesson? Uh, how physical methods can work to limit microbial growth, the disinfection process, what are antibiotics and how do they work, and have some sort of understanding of antibiotic resistance. Um, and hopefully, um, you have seen that it's really important to take your drugs on time, and hopefully, you have a new respect for taking antibiotics as you are done or as you're trying to get treated with some infectious disease.